Okay, now we are going to learn some more applications on the approximation theories related with the Taylor polynomials. So before coming into this section, you should have a good idea about the things that we did on previous section. So I would highly recommend you to go over those material first and to have a good grasp on that one before learning this actually these are not new theories, it's just some more applications. Okay, and also you should have a good idea about the series approximations as well, right? Okay, so let me remind you about the basic structure of Taylor polynomial. Now this is the function, fx is the function, this is the Taylor series, and this is what we may call it as the nth degree Taylor polynomial. Here you have only up to the nth power. And also when you extend this Taylor polynomial, when you take the limit of this Taylor polynomial to infinity, you should get the original series, because this is kind of a partial sum. So you should get the original one when you take the limit up to the infinity. Now I did not mention this specifically in the previous video set, but it's kind of obvious because this is kind of a partial sum in the original series, right? Okay, and now let's directly go to this question. It says approximate the function fx equals x, the cube root of x by a Taylor polynomial of degree 2 centered at 8. Now before going now first of all let's try to write down the Taylor polynomial of this function centered at 8, and since they have asked to write the Taylor polynomial of degree 2, that means we need to find t2x, right? So what we need is this one, and if you can't understand why this result holds true, you must go over the previous lecture videos and get a fundamental idea of the theory behind this one. Okay, right. Now that means we just have to find the first derivative and the second derivative and evaluate them at these given points. Now this 8 is there because we are supposed to find the Taylor polynomial centered at 8. Okay, so when you evaluate these ones by using this function, the cube root of x, then you can once you figure out the exact values for these derivatives and when you evaluate the derivative at these points, you will get this one. So in the first question they just asked to approximate the function by the Taylor polynomial of degree 2. So in other words, what they say is to write down the function, to consider this function as the Taylor polynomial of degree 2. Now the original function was the Taylor series, which is this one, and that had infinite number of terms, but now we are going to suppose that the function is equal to the Taylor polynomial of degree 2. Now this is our approximation. We are doing this because they have asked us to do so. And now let's see what will happen if we plot the graphs, right? Now this is the graph of the original function fx, right? And then if we plot the Taylor polynomial of second degree, which is this one, if we plot that graph, it will look like this. Let me zoom out. see, it will look like this. Now the red colored graph is the original function and the green colored graph is the second degree Taylor polynomial. And you can see that in this region, within this region, and if I zoom in one more time, see here in this region, the two graphs overlap with each other. In other words, we can say that within this interval, the x values in the, like when we substitute the x values on Taylor polynomial as well as in the function, in the original function, both outputs will be more or less the same, right? So that means if we consider this graph, and for the points in this let's say, let's choose this region. So for these x values, when you substitute it in the Taylor polynomial, which is the second degree Taylor polynomial, as well as in the function, this is the original function, if we substitute these x values, these, let's name it as x naught, then both Taylor polynomial as well as the function will give a very accurate, it will give outputs which are very close to each other. But say for instance, if we choose an x value somewhere here, let's name it as x1, then there will be a very big difference between the actual value and the value you obtain by substituting it in the second degree Taylor polynomial, and these two are not at all equal, right? But here it's very much close to each other. So basically what we can say is, for a certain region, this second degree Taylor polynomial will be a very good approximation for our original function. And here it asks, how accurate is this approximation when we choose x within this region? Now, to answer this question, you don't have to know the shape of these curves, right? But I drew these graphs only to give a better insight, right? So to answer this question, you don't need this image at all, okay, right? So here it asks, how accurate is this approximation when x is in between this region? So that means greater than 7 and less than 9. So it's somewhere in this region, right? So even in the graph you can see that it has a very good approximation, right? But if we zoom in there, if we keep on zooming in, see, it is not exactly equal, right? See, here you have some sort of a difference. See, when you zoom in, you can see that difference, but it's not a very big thing. See, in all these places you have a certain degree of difference, right? But it's not that significant when you compare it with these other points, right? Okay. So we know for sure that there will be a difference between the original function and the second degree Taylor polynomial. So we are going to find how accurate, what kind of an error that it has when you do the approximation with this second degree Taylor polynomial. So to do that, what we are going to do is, the method that we are going to adopt is a inequality that we used before. Remember, we did a condition, we went over a certain condition like this. If the n plus 1th derivative is less than or equal to a certain number, then the remainder for n will be, the modulus of the remainder will take this format. Now we did this as a theorem to prove the existence of a Taylor polynomial. But here in this case, we are using this same condition for a different purpose. Okay, now initially we introduced this result to prove the existence of the Taylor polynomial. Now if you don't remember, please go back and check over those videos related with this initial, with the introduction of this result, right? But here in our case, we make use of this result to prove, to come up with a solution for this question, to get a answer for this, to find how accurate this is when you choose x between 7 and 9. We make use of this result. Now the result is, if the n plus 1th derivative is less than or equal to m, then Rn, the remainder when you choose the nth degree Taylor polynomial. Now in our case, it should be R2, right? Because we are taking the second degree Taylor polynomial. So for this condition to be satisfied, we need the third derivative of the original function. Now the third derivative of the original function is this one, and we can see that if we choose x from that given region, if we choose x from this region, that is this one, you can see that the modulus of the third derivative of f, which is this one. Now since we choose x from here, you can just drop the modulus sign because x is anyway positive, and as you have a negative power here, it comes to the denominator, right? And you can directly write it as, the power, you can write it as positive 8 over 3. And then we know that when the denominator is increased, the whole value will decrease, and denominator is decreased, the whole value will increase. So the maximum number that you can get from here when x belongs to this one, this range, will be when x is equal to the smallest value, right? So here we have substituted the smallest possible value in our chosen region. So that means within this region, the third derivative of f will be less than this number, and if you use a calculator and find the answer, you can see that it is less than this number, right? So we can choose this as our m in the given condition, right? So now what we have is, we have a certain value that is an m value, which is 0.0021 in our case. So as we have this one, then we can directly say that the R3, no, not R3, R2, the remainder caused by the second degree polynomial is less than 0.0021 divided by 3 factorial x minus 8 to the power 3. Okay, so now we still have to do some work, because here you have a x minus 8 term. So if I write it separately, what we have at the moment is, we have the remainder caused by t2 will be less than or we can even say that it is strictly less than, let's have this equal sign for safety. What we have at the moment is this portion, that is 0.0021 divided by 3 factorial times x minus 8 to the power 3. And we also know that x is less than 9 and it is greater than 7, right? So if we subtract 8 from both sides, then you will get this inequality. Here you will get -1, here you will have x minus 8, and here you will have +1, right? And if you take the modulus, right, if you take the modulus, then it will be definitely greater than or equal to 0 because of the modulus, and since it is less than 1, this side will stay the same. So in other words, what we have done is, if x is within this region, then we have proved that x minus 8 modulus is less than or equal to 1. Therefore, we can directly substitute it in this inequality. So, ultimately what we have is the remainder caused by the second degree Taylor polynomial is strictly, it's less than or equal to 0.0021 over 3 factorial, that is this part, and instead of this one, now we can write down 1, right, because this is less than or equal to 1. So here you can multiply it with 1, right? So actually what we did here is, for this inequality we can write down a next step, keeping all these things constant, and as we knew that this is greater than 1, we can write another inequality for this term, and as you already have this one, you can compare the R2x along with the rightmost number, which is this one. So ultimately we have the remainder, or the error caused by the second degree Taylor polynomial is less than this number, and that is equal to 0.0004, right? So ultimately what we can say is, if we choose x between 9 and 7, that means if we choose x in this region, then the approximation in that we considered, this one, that is the red colored graph and the green colored graph in this region, will be accurate. Approximation in part A will be accurate to within 0.0004. That means the maximum error that it can cause is this much, right? So it's a pretty good accurate, it's a pretty nice accuracy that we have achieved, right? Because it's like it's accurate up to first 3 decimal points, which is a good number, right? So in other words, what we mean by that is, now if we go back to our original graph, let me zoom out. Now if we choose a number which is greater than 7 and less than 9, so let's pick a number somewhere here, and let's focus at this point, okay? And then we keep on zooming, see that let's have the corresponding y value in here, this y value, and the y value in the green colored graph will have a difference of at most 0.0004, right? So if the original function gives, let's say 10.1, 2, 3, 4, 5, then the second degree Taylor polynomial should give you, now when here this is, I have chosen a certain x from this region, okay, let's say 8. Now I am just giving some rough values, okay. Then the second degree Taylor polynomial should also give an accuracy at least up to the third decimal point, and from here onwards it can change, right? It's something like this, it can change, but it should at least have an accuracy up to the third decimal point.